Hello, Biology 1625 students. Melissa here. I'm here to give you a brief overview about Research Project A and how we're going to analyze the data that you've already collected. All right, so in Research Project A, you were making some assay of biodiversity, right? So you collected two different samples from two different time points, so a total of 4 sampling conditions. And now you need to compare them in terms of biodiversity. All right, so what is biodiversity? What do we mean when we say that word? Well, there's different ways to calculate it, but we are generally including 2 different concepts when we think about biodiversity, and those are species richness and species abundance. What that means is species richness. This is what a lot of people actually think of when they think of biodiversity. This refers to how many different species are present in a particular area or sample or whatever. But we also have to account for species abundance. So how many individuals of each species are present, as well as how many different species there are. All right, let's just do a quick example so you can see what I'm talking about. We have 2 biological communities here, or at least 2 samples that we've taken, and I just made this example up. Let's imagine that we were counting bird populations in the American Southwest. So on the right, we have community A. On the left, we have community B. And the question is, which is more diverse? All right, let's just sort of dive in. If we look at both of these samples, we're seeing 5 total species. So in both cases, our species richness is 5. However, we have differing species abundance between each of these communities. So based on that, which is more diverse? Well, in community A, let's look at that first. We have 7 cactus wrens, 1 burrowing owl, 4 phainopeplas, that's the blackbird, 2 roadrunners, and 2 vermilion flycatchers. In community B, we have 5 cactus wrens, 3 burrowing owls, 3 phainopeplas, 2 roadrunners, and 3 vermilion flycatchers. Okay, so which is more biodiverse given that they have the exact same number of species? Well, in this case, it turns out that community B is more diverse because species abundance is more even. Okay, so if we compare those numbers in community B, they're closer to one another than community A, which is pretty heavily biased towards the cactus wren. All right, so that's just kind of a qualitative way to think about it. Now we're actually going to calculate biodiversity. All right, so yes, this is math, but please don't panic or turn off the video. This is actually much simpler than it appears. All right, so let's talk through the equation. It's really not that scary, and then we'll calculate a couple of examples. All right, so this is the Shannon Index of Species Diversity. This is one of the most popular ways to calculate biodiversity. All right, so H is species diversity. H is equal to the negative sum of PI, which is the proportion of a particular species in a community. And then we're going to multiply that by the natural log of that proportion. Okay, sound confusing? It's not that bad. Let's work through an example together. All right, let's assume that you have 2 samples that you've taken. Now, of course, you're going to have 4, right? 2 samples from each location at different time points. But just for the sake of this example, we're going to make it super simple. 2 samples, and let's say that we counted 100 individuals. In sample 1, we have 60 individuals of species 1, 20 of species 2, 10 of species 3, 5 of 4, and 5 of species 5. Okay, let's imagine that in sample 2, we have 5 species as well, but we have a different abundance. Okay, so let's go ahead and start calculating diversity. So here's that equation once again, and let me just talk you through this. Okay, so here once again is the data that we collected for this sample. So just the number that we counted out of a total of 100. Okay, first thing we're going to do is calculate PI. Super simple. All we're going to do is divide the number of individuals for each species by the total number. Okay, so for species 1, we counted 60 and there were 100 total, so we just take 60 divided by 100 and that gives us 0.6. All right, we do the same for the rest and we get these numbers. Next, we're going to take the natural log of that number. Okay, this is just a button on your calculator, okay? So you're gonna type in 0.6 and press the LN button. You'll get negative 0.5108, okay? You'll repeat this for the rest of them. And then we're going to calculate PI times the negative log, or I'm sorry, towards the natural log of PI, okay, which is here. Okay, so we take the number that we previously calculated. That is that's the third and fourth column on this table. So 0.6 times negative 0.5108, and we get 0.3065. We'll repeat that for each species. So 0.2 times negative 1.609 equals negative 0.3218. 0.1 times negative 2.303 equals negative 0.2303. Okay, 0.05 times negative 2.996 equals negative 0.1498. Okay, repeat that again for species 5. All right, now we simply take the sum. That's that big E-looking symbol, okay? And what we're summing is that final column, all right, which I've just pulled down and put in equation form down here. Okay, so we just take the sum of all of these. We multiply the sum by -1 because it's the negative sum, and we get 1.158. That is our measure of species diversity. So that is H. All right, sample 2, we can do the same thing. We'll work through this one a little bit faster. So once again, this is the data that we collected, 30, 40, 10, 10, 10 individuals for a total of 100. Okay, PI, we simply divide that by the total number, which in this case is 100. All right, we take the negative log of PI, once again, just using our calculator to do this, and then we multiply PI times the natural log of PI, and we get the numbers in the final right-hand column. All right, just like last time, we take the sum of those 5 numbers in the last column. We multiply that by -1, and that gives us 1.419. All right, so now we have our measure of biodiversity for these 2 samples. By the way, we also have our measure of species richness, right? Because each of them had 5 species, so species richness in each case is 5. All right, now let's talk about how we want to represent that. Okay, so first thing we want to do, here's our data once again that we took, is we want to give some kind of like visual representation of these data. So we could do that in one of 2 ways. You can sort of pick whichever you like the best. I've put them both here. One is a pie chart, so that's below. We're showing sample 1 on the left and sample 2 on the right. And then the second is just above that, and this is a stacked bar chart, okay? So you can see that we're representing essentially the same data here. Our stacked bar is out of 100%, and you can see that those colors are proportional to the abundance in each sample. All right, so this is one thing that I want to see from you if you're analyzing Research Project A. Now, you're going to have 4 bars or 4 pie charts, right? Because once again, you took 4 samples, and you're going to have up to 15 different species, okay? And if they're not like identified to species level, that's completely fine. They could be by taxa, like maybe species 1 is rotifers, species 2 is green algae, species 3 is diatoms, okay? That's completely fine. We don't need to classify it all the way down to species level. Okay, next we want to see some measure of species richness. In this case, it is 5 for both, and diversity, which is the calculations that we did. Best way to show this would be in the form of bar graphs, okay? And so this is showing richness in both of these samples, as well as the diversity that we calculated using that equation. Okay, hopefully that helped. Please feel free to message me on Canvas if you have any questions about how to do this. Thanks, I look forward to seeing your results.